Of the ingredients used to modify the properties of coatings, the filler or extender pigment often plays a significant role. The term filler is misleading, implying a material intended primarily to occupy space and act as a cheap diluent of more costly components. The silicate minerals most commonly used in coatings, kaolin, talc, wollastonite, mica, and Nepheline syenite, truly serve as functional additives. They are used to optimize coating stability, rheology, and application properties, and to enhance dry film properties. The characteristics which determine the properties that a filler will impart to a composite are particle shape, particle size, volume fraction, and particle matrix compatibility. Particle matrix compatibility relates to the ability of the polymer to coat and adhere to the filler. The shape of most mineral filler particles can be approximated as a sphere, cube, block, plate, needle, or fiber. Some fillers contain a mixture of shapes. Mineral particles resembling plates, needles, and fibers are further characterized by their aspect ratio. For fibers and acicular particles, the aspect ratio is the ratio of mean length to mean diameter. For platy particles, it is the ratio of the mean diameter of a circle of the same area as the face of the plate to the mean thickness of the plate. There is probably no single property of fillers that is as misleading and misunderstood as particle size. A filler's technical description may contain a value, usually in microns, for median particle size or median diameter. This number is actually of limited practical value. The only three-dimensional geometric shape that can be unequivocally defined by a single number, such as diameter, is a sphere. The diameters of nodular and blocky particles are poorly related to that of a sphere. Platy and acicular minerals, particularly high aspect ratio types, cannot be defined in any literal sense solely by diameter, yet that is the way their particle sizes are routinely characterized. The equipment used for particle size analysis matches the behavior of a particle, regardless of shape, to that of an ideal sphere of specific diameter. Particle size is therefore conventionally reported as diameter, but the values reported are actually in terms of equivalent spherical diameter, or ESD. Particle size analysis is also complicated by different methodologies that base their calculations of ESD on different physical properties. The equivalence may be to a sphere having the same sedimentation rate, or the same volume, or the same mass, or the same surface area, and each will provide a somewhat different value. Particle size analyzers designed on different principles of analysis therefore won't necessarily provide comparable results, even on the same sample. For any given method of particle size analysis, particle size distribution data is somewhat useful for comparing the relative fineness of samples with similar particle shapes. However, particle size distribution rather than the commonly reported median ESD must be compared. The median indicates only that half the particles will have a larger ESD and half a smaller one. It says nothing about the size of the largest or the smallest particles, which can have a significant effect on filler performance. Neither the median ESD nor a particle size distribution can provide truly comparable results for two minerals with distinctly different shapes, such as calcium carbonate and acicular wollastonite. Fillers are often sold according to nominal mesh size. This can mean anything from 95% to 99+% through the indicated mesh. Mesh size indicates nothing about the size distribution of the oversized particles or the undersized particles. As with the data from automated particle size analyzers, mesh size of minerals with very different shapes will not necessarily be directly comparable. High aspect ratio particles, in particular, can be a challenge because a particle considerably longer than the mesh opening may pass through easily if its short dimension is smaller than the opening. At best, mesh size provides a rough relative comparison. Fillers usually exert their strongest overall influence on properties and cost when the volume fraction is sufficiently high to allow for the matrix to just coat all particles and fill interparticle voids. In coatings, a maximum filled matrix occurs at the critical pigment volume concentration, or CPVC. Film properties change markedly near the CPVC. At volume fractions less than the CPVC, the coating film contains more binder than pigments and minerals. This is generally favorable for gloss, adhesion, and resistance to abrasion, corrosion, and blistering. As the CPVC is approached and exceeded, the pigment particles progressively disrupt the smoothness of the film surface, causing light to be scattered and gloss to be reduced. The film surface becomes rough with pigment particles, and the film has a flat appearance. At pigment volume concentrations above the CPVC, there is not enough binder to completely fill the voids between the pigment particles. The film becomes more permeable, with consequent reduction in scrub resistance, stain resistance, rust inhibition, enamel holdout, and blistering. Regardless of filler size and shape, intimate contact between the matrix and mineral particles is essential, since air gaps represent points of zero strength. Thus, compound strength is improved by good wetting of the mineral by the matrix, and further enhanced when the matrix is adhered to the mineral surface via chemical bonding. Surface coating is therefore often used to optimize filler matrix compatibility and adhesion. Although a mineral to which any type of organic chemical has been added is commonly called surface treated, a surface treatment may be differentiated from a surface modification on the basis of functionality. A surface-treated filler is coated with a processing aid. A processing aid may or may not bond to the filler and does not bond to the matrix. It acts as a wetting agent to make the filler surface hydrophobic and more intimately coated by the polymer matrix. Surface treatments improve filler particle deagglomeration and dispersion and allow higher filler loadings. A surface-modified filler has a coupling agent durably attached to its surface by covalent bonds. The coupling agent is in turn bound to the matrix through chemical reaction or chain entanglement. The coupling agents used as surface modifiers perform the same functions as surface treatments, and in addition improve matrix adhesion, thereby improving physical properties as well as the retention of physical properties with environmental exposure. The most commonly used treatments and modifiers are the organosilanes. The general chemical structure of organosilanes is R-SiX sub 3, where X is a hydrolyzable group, such as methoxy or ethoxy, and R is a non-hydrolyzable organofunctional group. The organo group may be reactive toward the polymer matrix, or it may be unreactive and serve as a hydrophobe or wetting agent. Modification with organosilane depends on the ability to form a bond with silanol groups on the silicate mineral surface. Since the silicates that are successfully silane modified generally lack structural silanols, these are a result of the reaction of silica surfaces and adsorbed atmospheric moisture. The hydrolysis of an alkoxysilane forms silane triol and alcohol. The silane triol slowly condenses to form oligomers and siloxane polymers. The silanol groups of the hydrolyzed silane initially hydrogen bond with the silanol groups on the mineral surface. As the reaction proceeds, water is lost and a covalent bond is formed. The reaction of hydrolyzed silane with mineral surface silanol can ultimately result in the condensation of siloxane polymer, encapsulating the mineral particle if sufficient silane is used. Once the mineral is reacted with the silane, it exposes an organophilic or organofunctional surface for interaction with the binder matrix. Silane treatment levels are typically 0.5 to 1% on mineral weight. The silicate fillers most commonly used in coatings are kaolin clay, talc, wollastonite, mica, and nepheline syenite. Kaolin clay is available in a number of grades. Air-float clay is dry ground kaolin that has been air separated to remove impurities and control the particle size distribution. Based on its use by the rubber industry, air-float clay is further differentiated as hard clay and soft clay, which refers to its reinforcing effect in rubber, not its Mohs hardness. Hard clay has a median ESD of about 0.25 micrometers. Soft clay has a median ESD of about 1.25 micrometers. Water-washed clay, usually soft clay, has been slurried in water and centrifuged or hydrocloned to remove impurities and produce specific particle size fractions. Water-washed clays are often treated to improve brightness. This includes chemical bleaching and/or high-intensity magnetic separation to remove iron and titanium impurities. Delaminated clay is made by attrition milling the coarse clay fraction from water washing. This breaks down the kaolin stacks into thin, wide individual plates for improved brightness and opacity. Calcined clay is usually water-washed soft clay that is roasted to either partially or totally remove surface hydroxyl groups. Calcining increases brightness, opacity, oil absorption, and hardness. Kaolin clay is also available in surface-coated grades, as with sterates or silanes. The primary use of kaolin in coatings is as a TiO2 extender in water-based architectural paints. Calcined clays generally provide the best brightness, TiO2 extension, and dry hide. Water-washed and delaminated grades also contribute to extension and dry hide, as well as covering power and gloss control. The typical preferred uses by function of the various clay products is shown here. Talc products are processed using various combinations of dry grinding, air separation, and flotation, depending upon the quality of the crude ore and the properties required for the intended applications. The talc most often used as a filler is commonly called Platy talc. It is distinctly laminar and characteristically soft talc. Purity is typically greater than 90%, and filler grades are 325 mesh and finer. The value of Platy talc in coatings is derived primarily from its particle shape and surface properties. Although talc is hydrophobic, it disperses easily in aqueous as well as solvent-based coatings. Because of its shape, Platy talc can have a beneficial effect on paint rheology. It generally contributes to improved brushability, leveling, and sag resistance. It is normally self-suspending in paint vehicles and assists in keeping other pigments suspended. When settling does occur, it is generally soft and is readily redispersed. Platy talc improves the toughness and general durability of paint films. The talc plates tend to align with the coating's flow so that they are parallel to the substrate in the dry film. This creates a physical barrier to the transmission of moisture, thereby improving water and humidity resistance. This impermeability can aid, however, in the formation of blisters as any moisture or gases leave the substrate. Platy talc reinforces the dry coating film because of its alignment therein and its naturally high aspect ratio. This reinforcement makes the film more resistant to cracking or rupture in response to stretching and flexing, thus better insulating the substrate from the environment. The combination of barrier properties, alkaline pH, and reinforcement accounts for talc's contribution to corrosion inhibition. Its barrier properties also make Platy talc well suited for coatings used on porous substrates to control penetration. In liquid coatings, 325 mesh or 4 Hegman talcs are most commonly used. The micronized talcs, 6 Hegman or finer, are used for TiO2 extension, good low-angle sheen, and good burnishing resistance. Macrocrystalline varieties are preferred for their excellent flatting. Most filler-grade mica is first collected as flakes by flotation from ore that contains several minerals. Dry ground products are air milled from flotation concentrate that has been partially or completely dried. Wet ground products are ground in water using mills designed to delaminate the mica into flakes having a higher aspect ratio, sheen, and slip compared to dry ground mica. Micronized mica is dry ground to less than 20 or less than 10 micrometers in fluid energy mills using superheated steam. Mica does not delaminate quite as readily as talc, so it is somewhat harder, although still softer and less abrasive than most other fillers, minimizing its contribution to abrasion resistance. Its high aspect ratio and platy shape provide excellent film reinforcement, but at the expense of optical properties. The relative performance of mica as a coating filler is seen here. Fine ground and micronized mica is used as a functional filler in a variety of paint and coating formulations. As a platy mineral, it has beneficial rheological properties in liquid coatings and also helps reduce sagging. Mica reinforces the paint film during drying and curing, and as the film ages, it reduces the internal stresses from oxidation, thermal expansion, and contraction. Mica increases the film's flexibility and reduces cracking and checking, resulting in improved adhesion and better weathering. Film reinforcement therefore accounts for mica's utility in a broad spectrum of coatings, from texture paints to exterior coatings. Wollastonite is unique among filler minerals for its combination of white color, acicular or needle-like crystal shape, and alkaline pH. The structure of wollastonite is characterized by the repeating twisted 3-silica tetrahedra unit. The chains formed by these silica tetrahedra are connected side by side through calcium and octahedral coordination. Because of this chain structure, wollastonite tends to grow as acicular crystals and preserve acicularity on cleavage. The high density of the silica chains accounts for the mineral's hardness. Wollastonite surfaces in contact with water will hydrolyze to form calcium hydroxide, which accounts for the alkalinity of wollastonite slurries. Wollastonite has a strong buffering effect in acid solutions due to the release of calcium ion. The filler uses for wollastonite are dictated by the length of individual needles in the ore and the extent to which this shape is preserved during milling of the finished products. Powder grades are milled to a low aspect ratio, 3:1 to 5:1, either from naturally low aspect ratio ores or from high aspect ratio ores that have been ground in a way that breaks the needles. Despite their low average aspect ratios, powder grades can retain a significant portion of acicular particles. Acicular grades are produced from ore containing a suitably high percentage of long needles. The ore is milled in such a way that very fine needle-like particles are preserved and recovered. Acicular grades typically have aspect ratios of 12:1 to 20:1. Both powder and acicular forms of wollastonite are available with surface coatings, usually silane. In coatings, wollastonite is used for corrosion control, providing resistance to flash and early rust. High whiteness powder and acicular grades are used to ensure film integrity when exposed to physical and environmental assault. The acicular shape of wollastonite particles, even at low aspect ratios, reinforces coating films, providing both durability and flexibility, plus superior scrub and abrasion resistance. Acicular grades are used in thick build systems for mechanical strength and durability. Wollastonite is used in epoxy powder coatings because its low binder demand promotes smooth flow, water resistance, improved adhesion, and good chip resistance. Coarser, more acicular grades are used in primers because they provide a micro-textured surface with good tooth for finish coats. In decorative powder coatings, 10 micron and 400 mesh wollastonites are used to provide a smooth satin finish. In North America, typical nepheline syenite consists of approximately 25% nepheline, 55% sodium feldspar, and 20% potassium feldspar. Feldspar mineral structures are based on densely packed 4-member rings of silica tetrahedra, forming hexagonal and polygonal voids. The dense packing makes feldspars nearly as hard as quartz. Typically, Al3+ replaces one of every 4 Si4+. The resulting charge imbalance is compensated by sodium and/or potassium ions. Nepheline shares the feldspar structure, except that Al3+ replaces half the Si4+. Unlike feldspars, the sodium ion can be exchanged with hydrogen ion, making nepheline less acid stable. Nepheline will gelatinize in HCl, while feldspars will not. Nepheline can form only in a geologic environment deficient in silica. Commercial nepheline syenite deposits and the products made from them are consequently free of crystalline silica impurities. These deposits are exploited for their high mineral brightness and low level of dark mineral impurities. Commercial products are made by crushing, dry magnetic separation, and milling. Fine particle size grades are produced by air classification. Although the performance properties of feldspar and nepheline syenite are similar, low vehicle demand and resistance to abrasion and chemical degradation, the latter is more often used because it is silica-free, it is an effective alkaline in-can buffer, pH 10 versus 8 to 9 for feldspar, it is available in a broader range of fine grinds, 325 mesh to 1250 mesh, and it has generally higher brightness. Milled nepheline syenite is composed of angular nodular particles. This shape, with its low surface area, promotes easy dispersibility, low vehicle demand, lower than what would be suggested by oil absorption values, and the ability to achieve high loadings. The shape and size distribution of these particles can significantly improve the integrity of dried film through their ability to interlock and pack more tightly and rigidly than smooth-surface, spherical, or nodular fillers. Dry film durability confers crack resistance and, in combination with relatively high filler hardness, provides high abrasion, scrub, and burnish resistance. Shape and particle size distribution also promote flatting and uniform low-angle sheen. Nepheline syenite has very low tint strength, contributing minimal color at high loadings. Film reinforcement, chemical stability, and resistance to chalking promote high tint and gloss retention on prolonged exterior exposure. The low refractive index of Nepheline syenite allows for higher loadings in clear and semi-transparent coatings and stains.